Okay, we are going to solve a fairly complex problem, a gas turbine problem with a regenerator in it. It's problem number 8116 from the problem module. So let's see what are the information given to us. The air enters the cycle. This is the atmospheric condition, that's state 1, given to us completely. Mass flow rate is also given. So if we may write about state 1, we can already build up our state 1. Pressure is known, temperature is known, and mass flow rate is known. Okay, so let's see what other information are available. The pressure ratio is 10, which means P2 over P1 is 10, so we know P2, which must be equal to P5, P3, etc. The turbine inlet temperature is given to us, and regenerator efficiency is also supplied. We are supposed to find the thermal efficiency of the cycle and do a what-if scenario. We'll come back to this later. Let's make the problem even more complicated. Complicated by slapping in a compressor efficiency. Let's say compressor has an efficiency of 90%. So to tackle this problem, we have to renumber the states, because now we will have an ideal state. Says 2 is our ideal compressor exit state, and 3 is the actual compressor exit state, which means all other states has to be shifted by 1. 3 becomes 4, 4 becomes 5, etc. Now let's set out to find all the states and the compressor power, turbine power, heat inlet, heat input, heat rejected, etc. from the cycle. So let's begin with state 2. Let's quickly draw a TS diagram of the compressor. And we recognize that state 2 will be isentropic to state 1. The pressure at state 2 is 10 times 100. T2 over T1, we can use the isentropic relationship for perfect gas, which we have been doing quite a bit in all other problems. So therefore T2 can be obtained now. T1 is already given, 290, 10 to the 1.4 minus 1 divided by 1.4. And if we can calculate that, we will get T2 to be equals 560 Kelvin. Okay, how about T3 now? T3 is what? The actual turbine exit, compressor exit. It will be to the right of state 2. So this is 100 kPa line, and this is your 1000 kPa line. So to find state 3, we have to use the compressor efficiency. What is the definition of the compressor efficiency? The ideal compressor power, which is m dot H2 minus H1 divided by actual compressor power, which is bigger, H3 minus H1. And that simplifies to T2 minus T1. CP gets cancelled in the PG model. And because compressor efficiency is supplied 0.9 times T3 minus T1. So that gives us T3 equals T1 plus 0.9. Notice that this equation is valid only for the PG model. Whereas until this point we did not use any model, so this will be valid for also IG model. So this will give us H3 equals H1 plus H2 minus H1 divided by eta C. So this is a stronger relationship between 3 and 1 and 2, because this will work for any model, whether it's PG model or IG model or even PC model in the future. Anyway, to solve the problem manually, we will use this relationship for the PG model. T1 is known, T2 is known, T1 is known. So plugging them in, we get T3 equals, if you do the calculation, you'll get 590, approximately 590 Kelvin. Well, now that we know T3 and T1, we can quickly determine the compressor power. The compressor power will be simply m dot Cp T3 minus T1, 6 kg per second, 1.005, and T3 minus T1 are how much? Our T3 is 590 and T1 is 290, and that produces approximately a power of 1808 kilo. Okay, let's keep on moving. Now we'll go to let's jump to state 4. So to do state 4 and 5, just to put it in perspective of the TS diagram, so we have state 4 here and state 5 here. For state 4, everything is supplied to us. Pressure equals same as P3, which is 1000 kPa, and temperature is given to us 1500 Kelvin, the maximum temperature of the cycle. 4 and 5 is isentropic. In the isentropic condition can be applied again. So therefore T4 divided by T5, P4 divided by P5, K minus 1 over K, which means T5 equals T4 divided by, now P4 over P5 is what? P4 over P5, this is a 1000 kPa line, this is a 100 kPa line, so this is 10. Solving this, we obtain T5 as 776 Kelvin. So we can easily obtain the turbine power H4 minus H5, and for PG model it becomes CPT4 minus T5 times m dot. Substituting the numbers, we got 6, 1.005, T4 is 1500, 776, and the turbine power is about 4347 kilowatt. Okay, so to find the next state, that is, let's say state 6, we have to understand what is the regeneration efficiency. What does regenerator effectiveness means? Well, look at what happens in a regenerator. The compressed air is heated from state 3 to state 6 by the hot exhaust from the turbine at state 5. So state 5 is the hottest temperature. So how hot can the compressed air get? The answer is at the most to temperature at 5. That's the hottest temperature. But in any real regeneration system, T6 will be slightly lower than T5. So the effectiveness is defined as the rise in temperature of the compressed gas, which is T6 minus T3 divided by the maximum possible rise. And we understand because 5 is the hottest gas that enters the regenerator, T5 is the highest temperature we could have gotten in a perfect regeneration system. So this is the definition of a regenerator. So therefore, using this equation, we can easily get T6. T6 will be, if we manipulate this equation, will be T3 plus 0.7 times T5 minus T3. Okay, so we'll go out and write that equation in another page. So we are trying to find state 6. Obviously, it has the same pressure as P3. There is no pressure loss in the heat exchanger, and the temperature T6 is given by T3 plus the effectiveness times T5 minus T3, and we already know all these values. T3 was calculated as 560 and T5 was 776. And solving that, we get a T6 of about 711. So notice 776 could be the highest temperature we could have ever reached. Instead, we reached 711 K. Not bad. Last state, the state 7. We have found all the states. So how do you find state 7? Well, to find state 7, concentrate on the regenerator. If we do an energy balance on the regenerator, that will give us the unknown, because we know state 2, state 6, and state 5. The easiest way to do a heat balance on a heat exchanger is to think like there is a fluid which is donor, which is giving out heat, another fluid which is receiver, receiving the heat. As you can understand by looking at this diagram, the hot gas from the turbine exhaust is the donor, going from 5 to 7, and the compressed air from the compressor is gainer, or receiver, from 3 to 6. So the heat received by the compressed air is what? M dot H6 minus H3. So M dot H6 minus H, so let's do a heat exchanger analysis. So to find state 7 energy balance, we apply an energy balance on the regenerator, which is just a heat exchanger. So the heat that is picked up by the compressor is M dot H6 minus H3, and the heat, so this is heat gained by one fluid, and the turbine exhaust is at 5, and after the regeneration it is 7. So this is the heat lost by the hot fluid. Heat gained by the cold fluid must be equals heat lost by the hot fluid, and that gives us a formula for enthalpy. If we want, we can get a formula for enthalpy or temperature by substituting the PG model. So if we get both the formulas, for the enthalpy the formula will be H7 equals H5 minus H6 plus H3, and if we do for temperature, it should be T5 minus T6 plus T3. Substituting this number, T5 is 776, T6 is 711, and T3 is 590. and that gives us a T7 of 655. Okay, again we made the same mistake. We substituted a bad value for T6 here. So now we have calculated all the states. We can now easily calculate what is Q dot W dot net and what is Q dot in. W dot net is turbine work minus compressor work, and we can, so the net work is given by the difference between W dot T, which is 4357 or 56, and the compressor work, which is about 1808, and the net work becomes 43. The network becomes 2549 kilowatt. So how do you calculate Q dot in? Because we need that to find the efficiency. Q dot in, you recall, if you go back to the diagram, where is the Q dot in taking place? In the combustion chamber between 6 and 4. So it's m dot H4 minus H6. M dot six Cp T4 minus T6, and we substitute T4 and T6, and T6 is 590 if you recall, and then we get 4693, approximately 4693 kilowatt. So therefore the thermal efficiency is calculated. It is W dot net, what we pay for, and that turns out to be 0.543. But typically thermal efficiency is given in percent term, 54.3%.